and also from east to west. So 7 catchments with different annual rainfall and with gradient in temperature and rainfall. I will only show one example. It's the Don catchment in Sheffield area, the Midlands of the UK. And when we run the model, we can see that different emission scenarios and for different periods that the soil moisture deficit is increasing with time and with the emission level. Witness index is the degree of saturation of the soil, is also decreases with time and with the emission level. Potential evaporation and actual evaporation also the same, so we expect more evaporation over the time and with high emission. The other thing that we were looking at carefully is how frequently and how severe the future drought events, and we can see here from the baseline data of 61 to 90, that part of nowadays, to by 2080s that we are expected to see in the UK more frequent drought and even more severe drought. And when we look at the river flows or stream flow, also we expect under different emission levels in the UK that will have a big reduction in the stream flow or river flows, especially during the summertime, where actually we need irrigation most. And when we look at the groundwater recharge, it is also the same trend that under the high emission, we also expect to have a reduction in the recharge, and especially during the summer, where actually the groundwater is used also for irrigation, especially in the southeast of the UK. And in that catchment in particular, the water demand and supply also showing a gap, and that gap is widening as we move with time. In the 7 catchments, 6 of them, they show that big gap. Apart from Scotland, where the Eden catchment didn't show gap, and that's for several reasons. They are going to have more rainfall, and also there's no much population increase in that catchment. There are a number of references here that we published this data in recently. But how can we narrow the gap between the water demand and supply? There are several ways to increase the water, to decrease the gap. Is by increasing water supply is the number one. So we increase water supply by more surface storage, reservoirs, dams, more groundwater recharge, more wells, use of treated water or brackish water, desalinated water, and other solutions, including the increasing the water use efficiency of the irrigation systems. Water harvesting is one of them to increase our water supply, and we harvest water at different scale: small scale, mesoscale, and large scale or macro scale. At different scales, we harvest water in order to increase the water supply. And if now you look at the small scale from check dams, field ponds, rural urban tanks, this is example from India, and here is example from mountain lakes in Tunisia. This is Al Gawazin Lake in Tunisia, and 2, of course, the huge dams like the St. George's Dam in China. But also you can harvest water where the rainfall falls, and this example from Syria and Burkina Faso, where you have those ponds, and you can basically plant where actually the water accumulates for supplying the plant roots with some water. And this is another example also for harvesting water as they fall in Burkina Faso for using those says. And also you can save water under the ground by having here shafts where you can artificially recharge aquifer and then get that water from the tanks to irrigate the crops or the trees. The other thing is another example for saving water, storing water under the ground and using the underground dam. And this is underground dam from Brazil, where they put plastic sheets here in trenches and they close down the trench. And after they do that, you don't see much other than what you see here in the picture. And that's actually allow water not to be moved horizontally from one strip to the other. So it keeps the water within a single strip to supply the plants with some water. The other thing is that folk harvest, and that's actually quite a normal practice in where actually they have those fog collection nets, and you can collect the fog and save it for further use. Another thing, of course, is that the use of cloud seeding by using silver iodide or potassium iodide or frozen carbon dioxide, where actually they seed the clouds and they allow the rain to fall. But of course there is an environmental issue that these chemicals can affect the soil quality, and a new trial led by Royal University in the UK is actually to apply electric charge to the clouds and then would allow the rainfall to fall without having to use chemicals. Another thing that I tried with another PhD students is to harvest the dew water early in the morning at dawn time, and we can actually use a certain type of films to harvest that water and to increase our water supply. Another new technology came around led by a Czech technical university, and they can actually harvest the humidity of the air, and they can produce 800 liters per day when the relative humidity is equal or more than 60%, and they can harvest 800 liters a day if the relative humidity is less than 15%. And they showed that trial actually in Dubai in 2021. They use solar energy and they use the silica gel as an agent, and this technology uses only the solar energy, which is type of the clean energy. But also they use the irrigation for sandy soil after adding algae to the sandy soils to improve its retention capacity to keep the water. And that's the structure they are using now, or they are showing us they are using it in Dubai, and that can be linked to petrol stations here where people they can get petrol for their cars, but also they can get water from these units which harvest the humidity of the air. So there are a number of applications we published in rainfall harvesting. Now, increasing water supply by non-conventional water resources is a common practice, especially in the Middle East. And one thing is that we have a lot of brackish water, and the fresh water worldwide is less than 1%. And most of the water is saline water, and that's actually not well used in most of the world. But we started to use that in one of the EU funded projects, and we were able to grow tomatoes in Egypt and also in Syria. It's a tomato that's salt tolerant, and also we also applied that in Malaga for cherry tomatoes. And we can also see the bio-saline center in Dubai. They are using saline water to grow barley, pearl millet, and also alfalfa grasses for feeding the livestock. So you can also use that saline water in sequential use by adding the saline water here to the least tolerant plant, and then collect the drainage water and irrigate more tolerant plant, and then collect that water and irrigate more tolerant plant, and so on. And another type of water that we use is treated wastewater. And in Safir funded project, we have been looking at companies that can help us to have an in-situ treatment. And this is an example from a company produced in-situ treatment. It's called Prof. It's a Danish company. And they can make actually the treatment for 30 families and in a small community. And that water can be treated, and it comes as clear as that, and then can be used for drip irrigation. And here you can see it is like a shipping container, and the shipping container here is a system where the water goes from one side, comes to the other side as clean, and then be used for drinking water. The system here is that the water comes from this small community and then gets filtered. If there is heavy metals can be removed by ferric hydroxide filter, and then can be subjected to ultraviolet, and then you can also add fertigation dose to it and use it for irrigation. This is a good example of decentralization, because most of the treated wastewater wastewater are linked to big cities and away from the farming. And this is a good example. If really we are going to use wastewater for remote areas, we have to decentralize it from big cities and for in-situ treatment. Another thing that we need to look at is the improving water use efficiency. And improving water use efficiency is that we have to adopt a more modern, efficient irrigation system, minimizing losses by seepage, leakage, evaporation, automating the irrigation system. We need also to do more capacity building on the use of the new technologies, and also have to adopt policies on modernization of the irrigation system. If you look at the efficiency of the irrigation system, it goes from 70% at the reservoir, where the reservoir that loses a lot of water by evaporation, and most of the time it's about 70%. And then as it goes on during the conveyance, all the way to the farm, to the plant, and sometimes it goes to only 75%. And that's a very low efficiency. So we need to minimize the evaporation process. And this is an example here from the UK. Farmers, they group themselves and they cover their reservoir where they use it for irrigation by a solar panel. And that actually gives electricity for them, especially for dairy farms who are producing dairy products, butter, ice cream, and so on. At the same time, also, it allows them to pump water using the solar energy and reduces the evaporation losses from the reservoir. And also, you can cover the irrigation canals by solar panel to minimize the irrigation, the evaporation losses. And lining is another issue that we need to pay attention to. And I personally encourage the use of pipelines, because surface water is always subjected to evaporation losses. Pipelines is always a better and efficient system to use, and also not only saving water but saving land at the same time. But in the past year, we actually improved the irrigation efficiency by producing a new technology, and we moved from the basin to furrow to the sprinkler to the drip. So the efficiency started to increase over the past years. And we are in the center pivot system. Now we can see low nozzle sprinklers from the center pivot very close to the ground, and that's useful for saline water and treated water as well, and also to avoid any losses by wind. And we can actually save up to 30% of the water used by conventional center pivot systems. With drip irrigation system, also we moved from the classic drip irrigation system, where those actually wetted areas subjected to losses by evaporation and also salinity accumulation, to subsurface drip irrigation, which is better in terms of water safety. And recently we started to see rice cultivation now is using drip irrigation. And this is here an example of a good practice for rice in India, where the rice yield increased by 40% using the drip, water saved up to 70%, energy consumption saved by 60%, increased efficiency of water and fertilizer by up to 80%. So this is a good really example for moving from added rice or flooded basin rice to a drip irrigated rice. Another thing we started also to look at in one of the EU funded projects, Water for Crops project, and we started to irrigate only half of the root zone at one time, and the next irrigation we irrigate the second half. So we irrigate here the first half and then the second irrigation using a twin pipe, irrigation pipe under the soil surface. So it is a subsurface drip irrigation, twin pipes, and the plant is in between, and we irrigate only half of the zone at one time. And we actually applied that in one of the EU funded projects. We could actually save 26% by using a PRD, partial drying method, compared to the regulated drip irrigation. And also we could save up to 44% when we compare that method with the sprinkler irrigation system. So using a nano irrigation is something appeared recently, and here we are using a very low rate of irrigation. irrigation water and continuous. And we're using perforated tubes, and these perforated tubes with very small holes that can be used as semi-permeable membranes, and it gives you a very little amount of water and continuously from a very tiny nanometers pores. And this example here from a project funded by European Commission, and from in Morocco, where actually they use these perforated tapes and as a nano irrigation technology. Another aspect of that nano irrigation is that the amount of water that you use for surface irrigation for one tree, if you use nano irrigation, you can actually, the same amount of water can be used for 4 trees. So you can save almost 75% of the water. Another system started also to come to use now is the ultra-low drip irrigation system, where the flow is between 0.1 to 0.3 liter per hour. Normally, the drip irrigation conventional well between 2 and 4, and that's actually 0.1 to 0.3 is a low. And what actually you see here, this is the conventional drip irrigation where the water still goes below the root zone, and that's sort of losses we should avoid. But with the ultra-low drip irrigation system, you can see here this is only the water restricted to the root zone and nothing lost there below, and that gives us excellent water saving up to 30%. Another new technology came also recently is the varying irrigation rate VRI technology by the Valley Technology Company, where the nozzles of the center pivot, they don't really irrigate with equal amount. For example, if you have a light soil and ditch and heavy soil, then you will expect it to irrigate more for the light soil part, and you don't need to irrigate over the ditch, and you will irrigate less under the heavy soil. So you vary the rate of the center pivot system, and you end up sometimes with having that sort of mosaic that not every part irrigated the same amount of money. It depends on the type of the soil, the type of the crop at the same time, and that actually saves a lot of water. Now, water saving also can be done by the accurate estimate of the crop water requirements, and this is a big issue for the irrigation practices, where people actually they don't really know how much they should apply. And in the beginning, we started to use the Class A plan, where you can, from the losses, calculate how much you should irrigate. This is in the olden days. And then once the weather stations developed, a lot of equations came for us to use this data from weather station to calculate the evapotranspiration, and then we apply the amount equivalent to evapotranspiration. And the most used equation right now is the Penman-Monteith equation, and it is the modified version of Penman-Monteith by FAO in 1998. So this is the equation by Penman-Monteith, the original one, in 1965, where they put here for the first time the assembled or representation of the plant, which is the canopy resistance in the equation. So that was the first equation, came to add to the weather parameters. One parameter represents the plants, the stomata conductance or the canopy conductance. But that was quite difficult for people to find or to measure. And then the FAO with ICRE, they came with a simplification of the equation by assuming the canopy conductance or stomata conductance is equal to 70 seconds per meter as an average seasonal value. However, the assumption here, assuming this a fixed value for the whole season, it doesn't really represent the reality, because in reality, the stomata conductance it varies during the day and also during the season. So when they simplify that, we see now the equation when the FAO frequent ICID applied estimated conductance fixed value, one value per season, 70 seconds per meter, and became like this, and there is no here estimated conductance or estimated resistance as input in this equation. However, we tried in our project for crops in an experimental area in north of Italy, in Bologna area, and we applied the hydrocovariance and centimeters and also the Cosmos to look at how can we accurately estimate the crop water requirements and the irrigation amount. So we started by using the hydrocovariance, and here with those sensors here we started to look at the horizontal flow of vapor here using those eddies, and we our airflow, and we can calculate the actual evaporation, not the potential, but it is the actual. And then we used another technology, it's called the scintillometry. And scintillometers here you have a transmitter and the receiver, and we use infrared between the transmitter and the receiver, and the beam here actually gets subjected to the change in air density due to the temperature and relative humidity because of the evaporation under that, and that actually method can measure the evapotranspiration actual over 10 kilometers. We tried that in Crete and we tried that in Bologna, and it is one of the most promising technique for area-based evapotranspiration. And we look at the footprint of the scintillometers and hydrocovariance, and we analyze that. We will be taking into account the prominent wind direction. And we can actually divide the total amount of evaporation to see the contribution of each crop under the transit or under the area measured. And we can here see from that graph that we can see how much the wheat contributes to the total evaporation, how much the maize, the tomato, and the others under the transit. So you can actually see how much contribution each crop to the total evapotranspiration. When we put actually that measurements by centimeters and hydrocovariance into comparison with the ET node calculated by the Penman-Monteith's modified version FAO 56. This is the reference evapotranspiration, the continuous line, and also we calculated the crop evapotranspiration by multiplying the ET node reference evapotranspiration by the crop coefficient Kc, and this is what you see here as the yellow dots. If you compare these with the measurements of the hydrocovariance and scintillometers represented here by the blue and the orange points, you can see here that the actual crop evapotranspiration measured by the hydrocovariance is 45%, and by scintillometers 34%, compared to what we calculate by the equation. So it means that the equation overestimates or double estimates the crop water requirements. It means that for those who are using this equation, they should be aware that they are adding double the amount of the irrigation. And why is that? It's because the ET node or the evapotranspiration, they are coming from meteorological data. And the meteorological data produce potential evapotranspiration that would represent the atmospheric demand for water rather than the crop demand for water. The other thing, the accurate crop water requirements should be based on crop demand rather than atmospheric demand for water. And there were some indications by other researchers who found also comparing the hydrocovariance with the similar method in India. Also they found there is higher estimation by crop water requirements estimated by the FAO 56, and also in Jordan Valley, and also hydrocovariance measurements show that 36% lower than those reported by FAO equation, and also in Portugal a similar equation also FAO was used in comparison with hydrocovariance, and also they found that this equation overestimates, and possibly because of the simplification of the smart conductance by assuming the conductance is a flat line and one value per season and that caused actually maybe some errors in the calculations. Estimating group water requirements requirement using another method, soil moisture deficit observation. And in order to use the soil moisture, in the past we used soil cores, we used neutron probes, we used profile probes, and also we used ERT, or electric resistivity tomography. And recently we used the Cosmos. And here when we use the ERT, electric resistivity tomography, we use transects. And these transects, with some electrodes, we can actually measure the variations of the soil moisture in the field. And we can see the soil moisture here represented as 2D, and we can see the variation in the soil and variation in the plant reflection on the soil moisture. And you can also see here under drip irrigation, and here this is a trial between two types of the drips, regulated drip irrigation and PRD, partially drying method. You can also see how efficient the distribution of water under different irrigation systems. And the Cosmos here, new technology, is a new technology with the principle that fast neutrons are generated naturally at the land surface by energetic cosmic rays. This is a natural cosmic rays that comes from outside of the Earth planet, and actually it hits the surface here and interacts with the biosphere of the Earth, and that creates the neutrons, which has the same weight as the hydrogen atom. And then that actually creates those neutrons, and when the neutrons hits the hydrogens, or this H2O, then the speed or the velocity of the neutron gets slowed down, and we count in the device how many of those neutrons slowed down, or how many still fast, and then gives us indication about the soil moisture content of the soil. And this is really the system here. With those tubes, we can count actually how many neutrons they are really slowed down when they hit any source of water in the soil. It is a system with a large scale, can measure soil moisture content at 300 to 700 meter radius of sensitivity. So here we are talking about area-based. We're not talking about point-based, to avoid heterogeneity in the soil. And it's non-invasive, completely passive, uses background fast neutrons generated by cosmic rays, which are scattered slowed by H atoms. Gives a more representative soil moisture based on area, not on a single point. Could help to obtain soil moisture deficit to estimate irrigation water requirements for more area representative integrated soil moisture and avoiding point scale measurements and heterogeneity. We are using this actually now over the whole UK, the system, and also we started to apply that in India and in China as well. So we have a large network of Cosmos stations, and when we compare that in the field against the profile probes, against sensors, against soil cores, and we managed to get a good matching between the Cosmos and all these methods with a very small relative error here in the soil moisture. And this is an example of what we obtain. Here we have the soil moisture obtained by the Cosmos, and this is the rainfall, and you can see here it reacts very well to any rainfall. So it's a very fast reaction to the presence of rainfall. And here we calculate the soil moisture deficit, and we can make it color coded. So when it's red, it means that you need to irrigate. It's really highly stressed crop. And when it's green, you don't need to irrigate. And when it's amber, it means that moderately under stress. So that can be used really to operate the irrigation system. So this acknowledgement of my contributors and these publications. And actually when that work was published, there was a press release by Wiley about that important finding and also important water saving. So now I can talk about not only using non-conventional water, but also we need to use non-conventional crops, because they save water, and also the drought and salinity tolerant crops. So what we need to use? We need to use this water consuming crops, drought tolerant crops, salinity tolerant crops, use rotation of shallow rooted crops, followed by deep-rooted crops. And the reason for that, the deep-rooted crops will take the water and fertilizers actually left over from the shallow crop, and heat and cold water crops and wind-tolerant crops. And this example of two crops we used in a project funded by EU, SWAPMIT, and this is quinoa and amaranth, and we have been using these as cereals in different countries, Turkey, Morocco, Tunisia, and the UK as well. And we need biotechnology in addition to using this. We need biotechnology to increase the agricultural production. And the reason for that is the water scientists are not the only ones responsible for water and food security. Collective efforts are needed from agronomists, soil scientists, and biotechnologists. And if now you look at the beginning of the century here, that we had tomatoes here, the number of varieties in 1903 were 408. In 80 years' time only, we have only 70. And this is really a loss in biodiversity. And also, if you look at corn, sweet corn, 307 varieties in 1903. After 80 years, now the corn, 12 only varieties. So we are actually having loss in biodiversity and loss of varieties. And that's actually led to that Darwin to say it isn't the strongest of the species that survive, nor the most intelligent, but the one most responsive to the change. So we need the biotechnology to help us to increase the abiotic stress, and also to increase the yield. That's why the biotechnology is needed. So we need the biotechnology to help us to improve food security by developing new varieties with higher yields per unit of water. For example, crops with comparable yields but shorter growth periods. We need to develop crops with drought and salt tolerance with high harvest index. We need to improve the C3 crop efficiency, photosynthesis efficiency, to the level of the C4 photosynthesis efficiency crops. So we need deeper and wider rooting system. We need high photosynthesis efficiency. We need weatherproof against drought and flood and cold and heat. We need shorter growing season. We need crops that do not need to be replanted. And this example from Water for Crops project, where we, in one of the universities in Italy, Milan University, we're a member of the project, where they were trying to grow a corn that grows in Canada in 2 months, all season. It takes only 2 months in Canada. They were trying to see if it can be adapted to the Italian climate. So we are looking into a shorter season crops to use this water. And here is an example from Australia, where they are able to identify through the biotechnology the gene that actually improves the soil salinity, to improve the salinity tolerance of the durum wheat. And they managed to use the ancient Persian from Iran, a variety that's salt tolerance. They managed to identify the gene and to produce durum wheat for Australia that's salt tolerant based on this biotechnology. In the UK, we started now to use something they call it conventional tillage, and also we use agro-environmental wildlife strips. And the Ministry of Irrigation and Fisheries, of Agriculture and Efficiency in the UK, actually they financially reward farmers who are willing to use the edge of the field to grow wildlife strips, wildflowers, for example, and that's to encourage pollination. So the field management here is important for food security, suitable tillage practice, conservation tillage and mulching, leveling, plowing, manure application and weed control, precise inputs, low inputs, precision agriculture. Monitoring system, we need monitoring system, sensors, drones, and we are using drones now to identify if the yield has deficiency in nitrogen or other nutrients, and also we can use the drones from the images we can identify if there's a disease or any water nutrient deficiency, and also on the reservoirs we can use the drones to check on the quality. Any change in the color of the water in the reservoir can be picked up in the images by the drones. The agro-environmental wildlife strips at the edge of the field is important to enhance pollination rate, and we have here a good example near Oxford, Shire, where I live. It's called the Sheep Row Farm, and the farm is managed to show how farming and wildlife can coexist in perfect harmony. And also we are using now different way of also cultivation. We are using mixed cropping. So we have two crops on the same land, as you see here on that slide. And also we have here a companion crop. So you can have a companion crop like oilseed rape and legume as a companion crop to enhance the next wheat crop yield by fixing some nitrogen in the soil. Conservation tillage is very important to reduce soil evaporation, increase organic matter, reduce soil erosion, reduce agrochemicals, labor, and improve wildlife. And the conservation tillage also improves soil biota, soil structure, air filtration, and water retention. In conclusion, that water and food securities under climate change require integrated management that includes 1. Water resources management that accounts for impact of climate change, increasing water supply to narrow the gap between water supply and demand, encouraging the use of non-conventional water resources under suitable management, enhancing water use efficiency, reduce losses, nano irrigation, variable rate irrigation, partial drying method irrigation, automation, and more. Estimating accurately the irrigation water requirements, encouraging the use of non-water consuming crops, non-conventional crops, encouraging the use of precision agriculture and precision irrigation, encouraging the use of models as management tools, and develop mobile apps friendly and easy to use by farmers. Encourage the biotechnology and its application for food security, and enhancing land management like mixed cropping, conservation tillage, agro-environment, wildlife, strips to increase the yields. There are several approaches to deal with the issues of water and food security under climate change, but we just need to select the right solutions. Thank you, and I wish you a very successful conference.